Yeah, thank you very much for the introduction. Good morning, everyone. Thank you for getting up early to look at our latest data, new targets and technologies. I put in quite a lot of colorful images just to help everyone wake up and have a smooth start into this day. And with the first slide, I want to just also remind everyone of what these challenges are for CAR T-cell engineers in 2019. We've seen similar lists quite a few times, but just to go through it again, of course, identifying and validating novel targets that we can target with CAR T-cells, this is important. Identifying where in the clinical treatment algorithms we would implement these treatments is a key challenge. But also still understanding how these synthetic CAR receptors really work at the molecular level is a key aspect, and I'll show you some approaches that we've taken to really drill down at understanding how do these CAR receptors recognize antigens, how do they generate signals, and how does this then translate into the clinical response that we're trying to accomplish. And of course, increasing availability for cancer patients in need is a key aspect, and I will show you what we're doing about this. So the first story I want to share with you really started with the data that Dr. Garfeld introduced yesterday, and this is with treating myeloma patients with CD19 CAR T cells. And I think the entire field was kind of very interested, but also struck by these data showing that in the series of 10 patients, you could in fact induce partial and complete remissions with CD19 CAR T cells, even though you could not really detect the target antigen CD19 on the primary myeloma cells in these patients, as best illustrated by this flow plot showing that the percentage of myeloma cells where you could detect CD19 was 0.05% only. Still, these patients had a response, and some of these responses continue to be ongoing. And what this really put up as a question is, is CD19 maybe expressed at a very low level that we cannot detect with flow cytometry, but that is still sufficient to actually trigger the CAR T cell? And so the Pandora's box that this kind of also opened was the question, what is the antigen threshold that the CAR T cell needs to trigger? And we've seen some data that we obtained with our colleagues in Vienna yesterday using this Bilayer platform showing that the CAR T cells are indeed sensitive, maybe not as sensitive as TCR-restricted T cells, but very much along the lines also earlier work from David Stone, for example, that showed, okay, CAR T cells, they can recognize tumor cells if they express high levels of antigen, low levels of antigen. He also teased out that the CAR T cells are probably more sensitive, this is the antigen scale here, more sensitive than antibodies and bispecific antibodies, and that probably there are also differences in sensitivity between CD8 and CD4 T cells. More importantly also, there seem to be thresholds for inducing different functions of T cells. For example, inducing cytokine production requires probably more antigen on the surface of a target cell compared to inducing lytic activity, which has been presumed to be in the range of less than 1,000 molecules. And the challenge that then occurred is that with the conventional detection methodologies that we have, we cannot really determine in this range of 1,000 or 100 molecules if this is really the antigen density, because even if you attempt with quantitative flow cytometry kind of extrapolate into this area, flow cytometry does not have the resolution to really tell us, well, are there only maybe less than 100 molecules on the surface of this target cell. This is why we teamed up with Markus Sauer, the biophysicist in Würzburg, and he has all the latest technologies in super resolution imaging, and he recommended us to do what's called DSTORM, direct stochastic optical reconstitution microscopy, to obtain single molecule images of myeloma cells and look at whether there is CD19. So we actually obtained then a series of primary bone marrow samples from 14 patients. This is the typical image that you see by flow cytometry. So there are patients where you can clearly detect the CD19 positive myeloma population, but this is a rare event by flow cytometry. Some patients, there's a small population of CD19 positive, but in most patients, this is the image that you get. So there's not really a discernible CD19 positive myeloma cell population that you could classify with confidence as being CD19 positive compared to the isotype control antibody. So I actually started with this patient M012 and did this DSTORM microscopy technique, and we were readily able to identify CD19 positive and CD19 negative myeloma cells. Here are the cells. They're co-stained for CD120, 138 and CD38, so these are malignant plasma cells. The conventional fluorescence microscopy image looks like this, and then if you really zoom in with this DSTORM technique, you can really get a resolution where each of these dots represents a CD19 molecule. Here it's a counterpart. These are CD19 negative myeloma cells. There's some background here basically on the plastic layer where these myeloma cells attach, so you can do the staining, but in the area of where the myeloma cells is attached, you get a very clean image actually. So here are these 4 patients that I showed you as an example. So in this patient, also positive by flow, of course we see the CD19 positive myeloma cells. Also in this patient that has a small population of myeloma cells by flow, we can confirm this. Very interesting then, the patient 019 that was classified negative by flow. And in fact, with DStorm, we could readily detect CD19 molecules. And already appeared here that the expression level of CD19 in this particular patient was very low. Similar cases we've obtained, for example, on this patient M022. Also here, not really a myeloma cell population that you would classify with confidence as being CD19 positive by flow, but still by DStorm, you can visualize that there are myeloma cells that express CD19 at high levels. So we then, in the series of 14 patients, we detected 10 patients that actually contained CD19 positive myeloma cells. Only 2 of them had been predicted by flow cytometry. And again, looking at this patient 019 that has this very low expression, we found that in the end 80% of the myeloma cells in this patient are CD19 positive, even though they express the CD19 molecule at a very low level that cannot be detected by flow cytometry. So overall, the range of myeloma cells that was CD19 positive was between 10 and 80%. And again, only 2 of these patients had been predicted correctly by flow cytometry. So we then asked the question, is this expression of CD19 sufficient to trigger recognition by CD19 CAR T cells? And in order to do this, we first established these expression profiles here. So this is the patient that was very positive by flow already. So in this expression profile, you can see here, and this kind of beamer is not working. But you see this, it's a bimodal distribution. So you see the 19 positive myeloma cells and the 19 negative ones. We've colored in red the percentage of myeloma cells that flow cytometry had detected. Also here, this is the patient with the dim expression. You can see this clearly in this expression profile. We then co-incubated these myeloma cells with CD19 CAR T cells in vitro overnight. And what we find is that we get complete elimination of the CD19 positive myeloma cell population. In this patient who had a lot of 19 positive myeloma cells, after this 20-hour incubation, not all the cells are gone. If you let this assay run longer, they will completely disappear. Here we do the merge of these, and you see this fit, how we call it, that we put over these expression profiles in colored in red. This is the isotype staining. You see here again the 19 positive myeloma cell population, and you see that this completely disappears after the co-treatment with CD19 CAR T cells. The molecule density that we found here for myeloma cells in this red area that are CD19 high is in the area of several thousands of CD19 molecules. For these low expressors, you're in the area of a few hundred molecules. Interestingly, this case here we used to kind of extrapolate what is potentially the antigen threshold of CAR T cells for lytic activity. And if you do the calculation, we can say that these myeloma cells here in this patient that were CD19 dim, there were cells that contained only like 16 CD19 molecules on their entire cell surface. Still, they completely disappeared in this in vitro co-culture assay, indicating that under these conditions, the threshold for inducing lytic activity is actually even below 100 molecules per target cell. We've looked whether this can now be extrapolated also to other antigens, and we looked at CD20 also on myeloma cells. Here are the flow plots, 3 patients that we are included on this slide here. And also here with the DStorm analysis, we can zoom in and really quantitatively detect these target antigens, CD20 on the myeloma cell surface. And also here, if we do the treatment with CD20 CAR T cells now, we see complete disappearance of those myeloma cells which are found to be CD20 positive. So what do we conclude from these studies? The first thing, I think, where we can have consensus is that flow cytometry does not seem to be sensitive enough technique to detect low-level antigens that can still be targeted by CAR T cells. So I think in order to, when we evaluate patients for CAR T cell therapy, this needs to be taken into consideration. Also, what we're currently doing is we view this DStorm imaging platform as a platform to really analyze CAR sensitivity carefully, and also to drill down into defining antigen recognition thresholds of different CAR designs, both in killer and helper cells. What these data also suggest is that it's worthwhile to reconsider CD19 and CD20 as CAR target antigens in multiple myeloma, as there may be patients who have a high percentage of CD19 positive and or CD20 positive myeloma cells, and that may benefit from this treatment, either as a standalone treatment after autologous transplantation or in conjunction with other myeloma active reagents. So the way we're also taking this forward is to now do multiplexed analysis with this technique in a project called ImmunoQuant. Again, with Markus Sauer, the biophysicist, we can now do simultaneous imaging of multiple CAR target antigens. This is actually an example of when we look at Jurkat cells. We're also using this technique now to look at the T cells themselves, look at how the CAR is distributed and so on. And this is just to show you that we can look at 3 different target antigens simultaneously and do the cell counting. So I think this is a very interesting platform for us to also to do the immune monitoring and kind of look how tumor cells may evolve and change during the treatment course with CAR T cells. So the second part of the talk, I want to look at FLT3 as a target antigen that we're pursuing in acute myeloid leukemia. I think with all the data in B-cell lymphoma, also leukemia, and in multiple myeloma, I think the AML niche is still relatively underserved, and this is why we invested some effort into identifying potential CAR target antigens here. Of course, FLT3 is known in the AML community for many decades. What has been not really overlooked but paid less attention to is that it is a cell surface antigen, so it is an excellent CAR target. Already in this genetic analysis, you see that FLT3 is very highly expressed in every patient, at least as good as the alternative CAR target antigen CD33 and CD123. And you can readily detect FLT3 also on these AML cell lines, MOLM13 and THB1. Of course, what has been studied for many decades with regards to FLT3 is the fact that there can be mutations in the intracellular portion of this molecule, namely the FLT3 internal tandem duplication, that really constitutively activate this molecule such that it acts as a driving mutation for these AML blasts. Of course, recognition of AML blasts by our CAR T cells is independent from whether these mutations are present or not. However, we know that being FLT3 ITD positive is a bad prognostic factor. These patients have a worse prognosis than those patients who are FLT3 wild type because of this constitutive activation and this driving mutation that makes these AML blasts go crazy. We've confirmed that with our FLT3 CAR T cells we can very effectively eliminate these AML cell lines independent from whether or not they carry this mutation though. We've also confirmed very effective anti-AML efficacy against primary AML blasts from these patients. These patients were FLT3 ITD positive, and in this lysis assay you see there's a very rapid elimination of these AML blasts, similarly effective in this case as a CD123 CAR. In the mouse model, we inoculated these AML cell lines. They're firefly luciferase labeled, and you see that with a single dose of these FLT3 CAR T cells, if the CAR T cells engraft, we can basically cure these mice. So in the bone marrow, you will not detect any residual AML cells, and this is shown here. And we've confirmed this also to be the case with primary AML blasts that we can inoculate in these mice. They're then not firefly luciferase labeled, so you then have to sacrifice the mice at some point and analyze the bone marrow for residual cells. So this is very encouraging, but I think one of the lessons we've learned from the experience with targeting CD19 and other antigens, there is the chance for antigen downregulation or even antigen escape. So we've been wondering, is there a trick that we can play and force AML blasts to retain FLT3 expression, also in order to distinguish our approach from other strategies like targeting CD33, targeting CD123 in AML. And here's what we did. So we reasoned that because FLT3 ITD is a driving mutation and the AML blasts depend on the survival signal, if we treat these AML blasts with an FLT3 inhibitor, a small molecule that would decrease the survival signal, we would hypothesize that the AML blasts react by upregulating the FLT3 protein in order to sustain the survival signal, thereby, however, also exposing themselves to recognition and elimination by our FLT3 CAR T cells. And this would probably work best if these AML blasts express the FLT3 ITD driving mutation. So we first tested this on the MOLM13 cell line that indeed has this driving mutation. So here you see the FLT3 expression just baseline. And if you pre-treat them with an FLT3 inhibitor, in this example crenolanib, it's a second generation FLT3 inhibitor that still works also when these AML blasts acquire resistance to first generation substances like midostaurin. You see that already by flow cytometry you can easily detect this increase in FLT3 surface protein expression. Importantly, these are oral drugs, so when patients take these drugs they will get kind of oscillations in the serum levels, and this is why we wonder if we expose and re-expose AML blasts to this to crenolanib, will the FLT3 expression stay up, or can it still go up even after it's been modulated? So here's the baseline expression. Upon exposure, FLT3 goes up. If you withdraw the drug, it goes down. But if you re-expose the AML blast, FLT3 goes up again. So you can kind of play ping pong, and the important thing is these AML blasts don't get resistant to this. Already in vitro, you can see that after creno pre-treatment, this increase in FLT3 leads to stronger cytolytic activity. And so we eventually then went back to the mouse model and asked, is this really then a synergistic treatment? So here are the data. So if you don't treat these mice, the waterfall plot shows rapidly progressive deleterious leukemia. Crenolanib alone does not have a significant anti-leukemia effect. However, when we sacrificed the mice and looked at the FLT3 expression on these AML cells, we could confirm that also in vivo we had upregulated FLT3 on these cells. FLT3 CAR T cells alone, shown in green, are effective. So in a high percentage of mice, they effectively reduce leukemia burden. But importantly, when you then combine this treatment with crenolanib, you get a 100% response rate, and the depth of remission is superior to the single treatment. The mechanism of this, again, being the higher expression of FLT3 after creno treatment, and consecutively the superior engraftment and in vivo proliferation of our FLT3 CAR T cells. So we like this as an example of how CAR T cell immunotherapy and targeted therapy can be combined, and to our knowledge, this is the first demonstration as a new paradigm that these two treatment modalities can be combined synergistically in hematologic disease. We of course also here applied our DSTORM technology and confirmed that after creno treatment, FLT3 density is substantially increased on these AML cell lines, and we also confirmed this to be the case with primary AML cells. Of course, we're also interested in determining, is this a class effect? Is this unique to crenolanib, or can this also be accomplished with other FLT3 inhibitors? So we tested midostaurin, which is clinically approved, and it does lead to an increase in FLT3. Also, quizartinib, another second-generation FLT3 inhibitor, leads to this FLT3 increase, and is actually the substance that brings FLT3 to the highest level in these AML cells. And consecutively, we can show this cytolysis assay, cytokine secretion, and also proliferation. This is shown here in the bottom, and I'm sorry the beamer is not working. We see already in vitro increased reactivity of our FLT3 CAR T cells, and we're currently putting this through the mouse model to determine the optimal combination. So FLT3 is, in our mind, a very interesting target. It has a very clean expression profile. You see here the bio-GPS data. So in normal tissues, we cannot detect this. There's some literature out suggesting that FLT3 is expressed in cerebellum and in cardiomyocytes. So we're currently studying this. Here is stainings of a cerebellum, and at least in this microscopy technique, we cannot detect FLT3 protein, even though, as I said, other studies have investigated this by northern blot and apparently detected a signal. We cannot see this, and are therefore encouraged by these data, even though it's been known for a long time that FLT3, of course, is expressed on normal hematopoietic stem cells and hematopoietic progenitors. We confirmed this to be the case by flow cytometry. So these are normal hematopoietic stem cells obtained from several donors, and you can detect the FLT3. The expression is also quite uniform. It's not as high as on AML blast, but it's there. And of course, it also leads to elimination of a good portion of these normal stem cells in this in vitro killing assay. We then performed colony formation assays to determine, okay, there are some stem cells left here. This is shown in the in the upper graph, and I'm sorry the beamer is not working, but it does not seem to eliminate all of the stem cells. At least CD123 CAR T cells, they eradicate everything, but the FLT3 CAR T cells left some stem cells behind, and we wondered, okay, is there some hematopoietic potential that is preserved there, and there's at least some erythroid colonies that are forming. If this will be enough in a human to reconstitute or retain some amount of normal hematopoiesis, we don't know. However, there are clinical trials ongoing with FLT3 antibodies that use the exact same binding domain as our CAR, and clinically they do not see myeloablation. So we're still wondering what the best clinical context is to first use the therapy. Probably for a first-in-man clinical application, the setting that we would prefer is to identify a high-risk AML patient that is FLT3 IDD positive, use this cell product to get this patient into remission, into MRD negativity, then delete the CAR T cells and refer the patient to allogeneic bone marrow transplantation. And with further experience with the cell product, we could then also explore whether it's okay to use the cell product without subsequent bone marrow transplantation. In order to do this maneuver, so to delete the CAR T cells and then do the transplant, we heard yesterday that the conditioning regimen of transplantation alone may be enough to delete the CAR T cell product. Still, we have a depletion marker included into the cell product, EGFR-T marker, was already mentioned yesterday, first developed in Mike Jensen's lab. And the way this works is this is a truncated EGFR-T, so it's not transmitting a signal, it's also truncated in the extracellular portion, so it's not a sink for the growth factor, but it harbors the epitope for cetuximab, so these CAR T cells can be triggered and deleted with an antibody, Erbitux, that is available at every hospital pharmacy. We've recently reported and contributed to a study where we demonstrate that indeed administration of this antibody to mice that were engrafted with CAR T cells expressing this EGFR-T marker, you can delete these CAR T cells, as is shown here in the orange and the red plot. So within 2 or 3 days, these CAR T cells disappear. And in this particular mouse model, there was a CD19 CAR involved. Normal B cells came back and indicated the CAR T cells are really gone. And the toxicity, in this case B cell aplasia, was eliminated. So with these, I want to finish and close. So novel targets. FLT3 in our view is a very interesting target in AML. CD20 and CD19 may have a role, at least in some multiple myeloma patients. I will show you later today we have an alternative myeloma target, SLIMF7, that we're also exploring. Concepts for clinical implementation. So it may be that in some cases also these CAR T cells are indeed a bridge to transplant, as we've also heard for CD19 CAR T cells in ALL. These FLT3 CAR T cells may be an example in acute myeloid leukemia. And understanding the CAR T function at the molecular level and understanding how sensitive are these receptors, do we have techniques to really assess what the antigen threshold is. This will guide of course, the selection of target antigens for CAR T cells, but also guide studies of potential toxicities still during the preclinical development of these cell products. So with this, I want to thank the people in my lab, Thomas Nerreter and Hardik Chitani generated these data, support from German Cancer Aid. I want to acknowledge the German Ministry for Health and Education and the German Research Foundation with a clinical research center, GVH, GVL, that we're part of, and where the FLT3 work has its home. Thank you very much.
Thank you for this great data, Michael. To the first part of your talk, you showed nicely that there's also the possibility of complete elimination for cells with low CD19 expression. Do you go also from in vitro assays in vivo? What happens in the long term if a relapse appears in a mice, as an example? What is the nature then? Do you have a mixture between low and high expression, or does the low expression cells appear first? Is there anything known?
I mean, it's not so easy to model myeloma in mice, especially with regards to expression of low antigens. What we've been asked a lot is how does this correspond to the observation of antigen negative or low relapse, even when CD19 CAR T cells may still be around? Maybe a critical thing here is to consider that these very low levels of antigen, they may be enough to trigger lytic activity, but they're certainly not enough to trigger cytokine secretion, also not proliferation. So in a situation where your CAR T cells have basically contracted and there's a few cells in the memory pool, when you get relapse with CD19 negative or DIM leukemia cells or myeloma cells, this may not be enough to trigger re-expansion of these cells and then save these patients. Even though also in multiple myeloma, if there are normal B cells around that have lots of CD19, they can trigger also after infusion of this cell product the in vivo expansion and persistence that may be enough then to clear CD19 dim myeloma cells in the bone marrow. But looking at this is not so trivial because the in vivo models are lacking.
Are there other questions?
Maybe I misunderstood you, but you said that even with your very sensitive techniques, you found that 80% of tumor cells were positive, but that leaves 20%.
Exactly. So CD19 also with this technique is it's never a uniform myeloma antigen, and that's why we're currently looking at if you combine it with CD20, what is the percentage of myeloma cells you can address if you can define a combination of antigens that would cover 100% of the myeloma cells. This is ongoing. And that's why we say there may be some patients that may benefit from CD19 or CD20 CAR T cell therapy more than others, but most likely the cell product in myeloma would be used in combination with another anti-myeloma agent.
Hey, Stefan Mielke, Karolinska. Excellent presentation, Michael. I was just wondering about the myeloma, and you showed very nicely the critical minimal target antigen expression. There has been other mechanisms proposed, like depletion of B regulatory T cells, for example, immunological reactions. Would you mind to comment on them as well?
Yeah, I think it's absolutely right. I think also the mechanisms that led to this clinical response are not clear. They need to be carefully dissected, and we need to learn along the way. And ideally, we would be able to initiate a clinical trial where we stratify myeloma patients according to those who have expression, use the cell product, and then learn. But you're absolutely right. There's several mechanisms that are involved here and that are important.
Okay, I think we can move on.
Thank you.
Thank you very much.